Hi, pre-calculus students. We're in section 7.7 and we're going to be talking about finding the distance from a point to a line. Our notes consist of this bit of information. So we have a formula for finding the distance from a point to a line, and then we also have information about the relative position of the origin and how that affects the distance, or how we'll calculate the distance. So let's unpack this first formula that we have here. It says the following formula can be used to find the distance from a point, and the point is labeled x sub 1, y sub 1, to a line with the equation ax plus by plus c equals 0. So what that really means, if you have some point P, and we'll call that x sub 1, y sub 1. Let me go ahead and change my pen. So this will be x sub 1, y sub 1. If you have some point P and you want to know the distance of P to this line L, and that distance would be the perpendicular distance that we would be drawing. Let's see, there it is, the perpendicular distance from that point. We can use this formula, which is derived from the normal formula of a line. We can use this formula to find that distance, and I'm going to write that distance in there as t. So x sub 1, y sub 1 will be the coordinates of P, and then we would use that right in this formula. And C, it says the sign of C. The sign of C is really going to let us know which one of these we're going to use in terms of the radicals being positive or negative. So we'll use the opposite of sign of C. And so now what this section, or this particular rule, is giving us information about is this is a little different. This says, hey, if we are trying to find the distance, not even the distance, if we're trying to find the equation of the bisector of some angles, and so if you have two angles that, or two lines that intersect that form, two angles, two vertical angles, or what have you. Okay, so for instance, you have the coordinate axes here, and you've got these two lines, L1 and L2, that intersect each other. And so what this law is telling us is we have a way of thinking of a point on one of these bisectors. We can think of a point on one of these bisectors, and we know by definition, so the bisectors are really faint. I hope you guys can see it. So we can have a point on one of these bisectors. If you grab a point, you know that the distance, by definition of a bisector, the perpendicular distance from both of these guys should be equivalent, right? And then the perpendicular distance from both of these guys, I'm trying to make this perpendicular. Y'all are patient with me. I appreciate it. I guess that's perpendicular. You see what I'm trying to do? Let's pretend those are perpendicular and this. So we know that these distances should be equivalent. However, with our calculation, we can get a positive d or a negative d. So this is saying if the origin does not lie within the angle being bisected. So here's the origin here. Let me make it bright and big. There's our origin. If the origin does not lie, within the angle being bisected, or the angle vertical to it, then the distances have opposite signs. What does this mean for us? So if you notice that this origin is within, this, I'm trying to figure out how to say these lines, and therefore this point is within the angle in which the origin is within. Therefore, these d values are going to be equal. Let's call this d1 and this d2. But this angle does not have the origin in there. I hope this is making sense. This angle does not have the origin. Therefore, this bisector won't be in that same place. And because of the formula, we're going to get that d3 and d4, that's these two distances here, have opposite signs. That's what they're saying here. So d3 is equal to negative d4. It'll make more sense when we do the examples. And d1 is equal to d2 because of the fact that the origin is within it. All right, we'll see how this goes. All right, let's go ahead and take a look at a couple of examples. Okay, so we're just going to grab this formula and use it here. It says find the distance between 0.45 and the line with the equation as given. So the first thing we want to do is make sure we have everything settled exactly as it should be. So 4,5 is the point that we're dealing with, and the equation, we're going to write it in the form that we need to: 8x plus 5y minus 20 equals 0. Move that over there. And so now the next thing is just to simply find the distance. So the distance is given as a times x of 1. So that would be 40. No, it's not. That would be 32. Let me try that again. Actually, let me write it in. So if I put that in, a times 4 plus b 5 times y, which is another 5. And then we're going to add 20. Actually, we'll subtract 20 right there. And now, to figure out which sign, the sign of the radical is chosen opposite to the sign of C. So since C is negative, we're going to choose the positive radical values down here. Sorry about that being sloppy. Let's try it again. We're going to choose positive, and that's going to be a squared, which is 64. And then b squared, which is 25. And then so now it's just left for us to calculate. So now finally that's 32 plus 25 minus 20 over the square root of these guys. And so 64 plus 25 is going to bring us all the way up to 89. So we're dealing with the positive square root of 89 here in the denominator. So that's the distance. Let's go ahead and simplify this a little bit more. When I add all of this stuff together, I end up with 37 over the square root of 89. Mathematicians don't like radicals in the denominator, so rationalizing this, we get 37 root 89 over 89. And so that's going to be our final answer for that. Okay, so example 2 is now asking us to find the distance between two lines. And when we're dealing with the distance between two lines, generally it's going to be parallel. Because if they're not parallel, then it's not going to have a consistent distance. And in fact, if they're not parallel and we're operating on the same coordinate plane, they intersect. So there is no distance at a particular point. So these guys are parallel, and we can test it out by checking the slopes and seeing what we get here. So I'm just going to do that. So when I put this into slope-intercept form as the other line is, I see that we have exactly the same slope, and then so we need to figure out what the distance is. So let's take these two lines to be graphed somewhat like this. And the mistake I don't want you to make is for you to look at their intersection points and say, oh, well, the distance between their intersection points is the distance between the two lines. Because we know and we remember that the distance between the two lines will be the distance between them, their perpendicular distance. So a line that is perpendicular that goes through a point of one and another, that segment would represent the distance. So how are we going to find this? Well, this is just the distance that we were finding before. And what we'll do is we'll use this equation as ax plus by plus c equals 0. And we'll use this point as the x sub 1, y sub 1, or point P rather, that we talked about before. And so how do I know this point? How do I find a point? Well, the easiest way is to find the most convenient y-intercept. Most convenient y-intercept. And for me, that's the first equation, which is y equals 3x plus 4. That y-intercept is 0, 4. And so that's easy. Not that this would be bad. This would just be 0, negative 7 halves. If we were to use, let me do this in green. If we were to use this point and talk about this distance here, it would be basically the same idea. But I just felt like this was a more convenient point. So with that, we're going to go back to our formula and apply it to figure out how to find the distance, or what the distance is. So now that I've got my trusty formula by my side, I am going to figure this thing out. So first thing we need to do is make sure we have the equation in the form that we need it to be in. And so that equation of this second line with the 7 over 2, negative 7 over 2 is the y-intercept, has this formula that we want, or that form of the equation that we want. So 6x minus 2y minus 7 equals 0 is what we're working with. And then so our formula tells us to take point x sub 1, y sub 1 and plug it in. So point x sub 1, y sub 1 is 0, 4. And let's do the thing. So the distance is equal to that's 6 times 0 plus b, which is negative 2 times 4, that's the y value, plus c, which happens to be just a negative 7. All right. And then so now, no, not equal to 0. Sorry. And then now what we need to do is choose the sign of the denominator. The sign of the radical is chosen opposite c, so it's going to be positive as our c is negative. And then we're going to take the square root of the sum of a squared, which is 36, plus b squared, which is 4. And so the square root of that is going to be a positive square root of 40, square root of 40. And then this is gone, and then up here we end up with a negative 8 minus 7, which is going to be a negative 15 over the square root of 40. So of course we could continue with this answer a little bit by simplifying, multiplying top and bottom by the square root of 40, and we get negative 15 square root 40 over 40. This can be reduced and simplified, and we eventually get about negative 2.37, something like that. And your question and my question would be, why is this negative? Well, what this negative does, and this kind of relates to the next couple of examples, what this negative does is it tells me the location of the point is on the opposite side of the origin from the location of the line. Meaning I could touch the origin. If I were to start from the point and go straight to the origin, I could touch the origin before I would cross this line. If this line were closer to the point, or specifically if this line were on the same side as the origin is, right? Let me try it again. If we were to take this line and bring it up here, if we were talking about this distance here, our answer would have been a positive answer because both the line and the point are on the same side of the origin. What's the point in that? The point in that, no pun intended, is that we are going to accept the absolute value of 2.37, or the absolute value of the value that we got as the distance, because we're talking about, what the physical distance is, not really the location. We are at example 3. We're going to find the equations of the lines that bisect the angles formed by the lines 8x minus 6y equals 9 and 20x minus 21y equals negative 50. So the first thing I did is I went over to Desmos and I got them to graph the two equations. The red one is the 8x minus 6y equation, and the blue one is the 20x minus 21y equals negative 50. So we can kind of get an idea of what's going on. The next thing we need to do is think about what the bisectors look like and how that kind of relates to what we've been talking about before. So if you notice, these gray lines are going to be the bisectors, and what I'll do is I'll choose a point and create what is going to amount to a perpendicular distance. And what we know, if this gray line is the bisector, let's try that. You guys are with me. I know you are. If this gray line is a bisector, then both of these segments, D1 and D2, should be equivalent in length. And similarly, we should have the same thing here. If this gray line is the bisector of these two lines, or this angle created by these two lines, that's really what I should say, then I'm going to just choose a point here. Let me choose a better point. Let's choose a point here, and then we'll just talk about the perpendicular distance. Let's say it's something like that from these guys here, and I'll refer to these as D3 and D4. And so the length of D3 and D4 should be equal. However, that's not necessarily the case. We see that with the orientation of the two lines, and we talked about this earlier, if the origin is on the inside or in the interior of the angle that we're dealing with, then we know that the distances there will turn out to be exactly the same. They will turn out to be equal. You remember how we had the sign issue with the last problem because of the location of the point in reference to the line? Like sometimes it'll come out negative or positive. Well, that's what happens with this line here because of its location in reference to the point. The D1 and the D2 will be opposites. All right, does that kind of make sense? And so we're going to use that and the distance and the relationship between these lines that we have here to come up with the equation of the gray line. So what we have is the formula that we've been using before, and you'll see how kind of cool it is the way we apply it here. So check this out. We remember that x1, y1 is the point, and then the line that we're talking about is distance being distance that we're looking for it is ax plus by plus c. Well, so here's what we're going to do. We're going to call this point x sub 1, y sub 1. And we know that the two distances, whether it's the distance from this point to the blue line or the distance from this point to the red line, they have to be related in some way. And we know that D1, D2 in this case are going to be opposites of one another. So that's what we're going to do. We're going to find D1, D2. So if in looking for D1, let's start there. We know that D1 will be found because it is the distance from the point to the blue line. So the equation that we're using is going to be 20x minus 21y plus 50 equals 0. So let's go ahead and find that. Then we're going to find D2. You guys get it. Then we're going to find the distance 2, then D3, D4, and then we'll be able to use that information to find the equation of the line, okay? Okay, so this is what we get for when we calculate D1. Again, D1 is this distance here from this point, x sub 1. So let's go ahead and calculate D2 and see if that's going to give us the equation we need, and then we'll work on the other one in a moment. So calculating D2, we're going to have to set up our situation. So this time we're looking at the red equation, and we're going to be taking the distance D2 of this point, still x1, x sub 1, y sub 1, to the red equation, and we're going to apply the same ideas we did before. So D sub 2, let me pause you and let you guys catch up. Really should have said pause me so I could, keep you guys from having to watch me painfully write all this stuff out. So we get this is going to be 100, and then that's going to end up being 10. So then we get 8x sub 1 minus 6y sub 1 minus 9 over, and we chose the positive because the c value was negative, over 10. This thing is equal to this thing because these two lengths are equal. Well, they're not actually equal, they're related. I'll scooch up so you can see D1 is equal to the opposite of D2, so these guys aren't exactly the same. So what I'll do is I'll set them equal to each other, but I'll multiply this one by -1 because then they will be equal. Are you guys with me? And if they're now equal, then I can solve like a system of linear equations, and then I can find out the equation. All right, so I know that this has to be equal to the same thing, 20x sub 1 minus 21y sub 1 plus 50 over, and I'm just going to put 29 because I know D1 is equal to the opposite of D2. But check it out, I don't even really need the sub 1s anymore. That just was kind of anchoring me. This is now true for every x on that gray line. So every x, doesn't matter what kind of xy it is, every x has to have the same relationship, the same distance. The D1, D2 from every point on this line needs to be the same. So as I work on solving this, or really I'm not going to solve it per se, but I'm going to write it down so that we're really just dealing with one equation, and that equation is the one that we were looking for. So notice the sub 1s drop off, and now I'm going to, I guess it would be convenient for me to multiply this whole side by 29 and multiply this whole side by 10. I will spare you the boredom of watching me do distributive property, and I'll just show you what the answer is. Okay, so after a lot of fun, we got that this is one of the equations. So this would be the equation of this line right here. And then we have to do the same thing, finding D3 and D4, which happen to be equal, in order to find the equation of this smaller line here. And so we'll go through that right now. All right, so since D3 is equal to D4, and we are looking at this point here, and these two distances, I know it's pretty tiny, we're just going to kind of run through it like we did last time. I'm going to use x sub 2, y sub 2, not because it's that deep. I could do x sub 1, y sub 1 because you saw how we just got rid of it, but we're just trying to keep it in mind that it's a different point, and we're using it to demonstrate our understanding of the situation. So let's do that. Let's go ahead and set up the two equations that will be equivalent to one another. So we utilize some of the information from last time because it ends up being about the same. And we say, okay, these two are equal. Of course, we can drop the subscripts now, and we can continue on to make one equation, or really simplify the equation that we have so we can get the equation of the line. And with a little bit of work, we get that this equation here that has its distance being D3 and D4 is going to be this equation here, 432x minus 384y plus 239 is equal to 0. Or you can move the 239 to the other side. And notice I ended up dropping the x sub 2 because we're looking for all x's that have this relationship. All right. Okay, some pretty heavy stuff there. That was the bare bones of the chapter of this section. And after this, we are going to be having a test. So lots of formulas to remember, lots of concepts to keep in mind. Let me know if you have any questions about section 7.7, and I'll be happy to work with them with you and get to the bottom of the issues. Listen, guys, take care. Bye-bye.